Hello everyone, welcome to our lecture today. So in this lecture, I want to introduce how we can use the matrix to help us give the representation of relation. So in our previous videos, we already introduced how we can find or define a relation, and we also learn several special relation types. So they are the reflexive, symmetric, antisymmetric, and also the transitive relations. So then in this lecture, we want to continue on this topic and let's learn how to use matrix to show a relation. So here for this use matrix to show the relation, we have one requirement. This means for our relation, it needs to be a finite size. So we need this relation defined in a finite size. So this is the requirement for us to define to use the matrix to define it. Okay. And then what we can do for our matrix, actually we have 0, 1 matrix. So that means the value we can have for this matrix is only 0 and 1. 0 means this pile of the element is not in our relation. And 1 means this elements of AI, Bj is in our relation. So here A is the element from our side A and B is elements in our side B. Okay, so then let's continue here. So what we have is, so in our previous lecture, actually we talked about how we can use table to write a relation, right? So here in this part, actually what we have is similar to that one, but just use a more mathematical way to define it. So let me give one example here. So assume we have two sides. Side A has 3 elements, 1, 2, 3. Side B have 2 elements, 1, 2. And then what is our definition of relation here? This means the relation is defined from AB, and this means the relation is A greater than B. Okay. And then the question is, let us use the matrix to help us write down this relation. But before we do this, the first thing is, the question just give us a definition of this relation, but they didn't give us exactly what elements in this relation. So the first thing is we need to write down what is our elements in the relation. So for example, here I use R to denote our relation. And then, so for this one, if we have A equal our 1 in our side A, then is there any element in side B can smaller than 1? Actually, no, because for side B, we only have 1, 2, right? So there is nothing smaller than 1. So that means, okay, like elements in our A, it won't happen or show in our relation. And then the next, if we have the elements in side A that equal 2, then is there any element in our side B is smaller than 2? Yes, we have number 1. So here it means if A, here we choose 2 from side A and we choose 1 from side B, yes, we will have 2 greater than 1. So this is an element should in our relation. Then similarly, we should try like 2, 2. Okay, 2 now greater than 2. So this is not a pair we want. And then let's move to the next one. So now if we choose 3 from our side A, then look at B. Is there any elements in B smaller than 3? Actually, both will smaller than 3, right? 1 smaller than 3 and also 2 smaller than 3. So we will have 3, 1. This should in our side relation, and 3, 2. This should also in our relation. Okay, so now actually we find how many elements we have in this relation is 2, 1, 3, 1, and 3, 2. So now we know this is our definition for the for the relation, and then let's try to use matrix to write this. So here for this matrix, what we will have our row is shown as the elements in our set A. The column shows the elements in set B. So you can think like from like A1, we have A2, we have A3, right? And which is our 1, 2, 3. And we also have our B1 and also B2. So this is our number 1 and number 2. And then what we have, if this pair of the elements is in our relation, then we will write 1. Otherwise, we write 0. So here you can see 1, 1. Is 1, 1 in this relation? No, 1, 1 is not in our relation. We should write 0 here. And then how about 1, 2? Like A1, B2. So it's 1, 2 in this relation. 1, 2, no, it's not in the relation. So write 0 again. And then let's go to the next row. So this is A2, B1. So it's 2, 1. It's 2, 1 in our relation. 2, 1. Yes, 2, 1. This elements in our relation. So that means great. So now we will have 1 here for this one. Okay. And then for the next thing, if we have A2, B2, is A2, B2 as 2, 2 in this relation R? No, 2, 2 not here. That means here we should have 0. And then let's go to the next row. So now A3 as 3 and B1 as 1. Is 3, 1 in our relation? Yes, 3, 1 in the relation here. That means now we should have 1. Okay. And then if we look at the A3, B2, so it means 3, 2. Is 3, 2 also in this relation? Yes, 3, 2 is the last element in the relation. So that means great. So now we should also have this 1 as the last row, last column. Okay, so this is how we can create our matrix. And then, of course, for matrix, in general, when we learn in the linear algebra, right, we know we should have the square bracket to circled or say to bounded our matrix. So that means let me write this as MR. So I can say MR, which is our matrix for this relation. So we say this is okay. Let me write the square bracket here. So this is like this, and I will have also the right square bracket here. Okay, and inside this will be 0, 0 for the first row, and 1, 0, 1, 0 for the second row, and 1, 1 for the last row. Okay. Okay, so this is what we have, how to write of our matrix to show this relation. So we use this example to explain how we can write or find all of the elements of a relation if we just find a like description in English of the relation. And also we learn how we can use matrix to write down this. Okay, so hope this one is clear for everyone. And then let's look at the second example. So this example is how if we get this matrix of this relation, can we find what is the element in our relation? So here we have two sides, A and B, and the element in our side A is A1, A2, A3, and the element in our side B is B1, B2, B3, B4, B5. So they have 5 elements. Okay. And now our matrix is right as was shown in the screen. So then can we find what is the element in our relation? The answer should be yes. And then how we can do it? So let me explain this step by step. So now if we have this relation definition, and also about this matrix, the first thing is let me know here we have 3 rows and 4 columns. So as we explained in the previous example, so each row is show the element in the side A, and each column shows every element in our side B. So actually here we know for the first row, this should be mean for our A1. Okay, so this is for our A1. Let's write down this here. Okay. And then for the second row, this is our A2. And then for the third row, this is our A3. So this is A1, this is for our A2, this is A3. And for the column, this is B1, B2, B3, B4, and B5. Okay, so now we understand the meaning of each row and each column. So then we can find what's the meaning for each one. So that means if the element equal 1, it means this pair of the elements should in our relation. If the elements equal 0, it means this pair of the elements should not in our relation. So now let's check this one by one. So for our R, the first one, let's focus on the first row, is the second column. So if we look at this one, it means here this is this row and this column. So it means this is pair of A1 and B2. So what is that? So that means here in our relation, we should have A1, B2 is in our relation. Okay. And then let's look at others. So in the first row, we don't have any more one. So let's move to the second row. So the second row, the first one we find is in the first column. So now if we look at this one, we will find this is about A2 and B1. So for A2, B1, we have this is 1, right? So A2, B1 should also in our relation. And then the next thing, we have 1 here in our second row. So for this, we have this is still about A2. And now what is the column? So this is third column. So that means this is for our element B3. So now we have A2, B3. This position have also 1 in our matrix. So that means our A2, B3 should also in our relation. Okay, and the last one in our second row is from the 4 column 4. So it's for B4. So that means here we have A2, B4 also in our relation. Okay, so far so good. Okay, so then let's move to the last row. So the last row we have 3, 1 here. There are first row, third row, first column, third column, and last column. So this is shown for B1, B3, and B5. So, and for the last row, we know for this row is for our third element in A. So it means this is A3, B1. We have A3, B3, and also A3, B5. Okay, so now we find this is all of the elements in our relation R. Okay, so this is if we get this matrix representation of the relation, how we can find all of the elements in this relation. So that means first we need to know what is our definition of our set A and set B. And then we know each of the rows show the element in our set A, each of the columns show the element in our set B. So if there is a 1 in this position, then we will find the corresponding A and B in our set A, set B should in our relation. Okay, so hope everyone is understanding this part. Okay, so now we already know how we can use matrix to write our relation. And in our previous video, we introduced 4 types of important relation. They are reflexive relation, symmetric relation, antisymmetric relation, and transitive relation. So now if we have this matrix representation of our relation, let me explain how we can just use this matrix to help us check if this relation is satisfy any special requirement of special type of relation. So now you can see if we know this one, this is much easier than we use the definition of this special type to check the relation. Okay, So for the first one is reflexive. For reflexive, if we find all of the diagonal value is equal 1, then we know this is a reflexive relation. So why we have this? Because the diagonal, it means it's the elements with same, like if this is relation defined on like set A times A, right? So if we say the definition of our relation is defined on two sides, A times itself, then we will know this is our A1, and for each of row, this is our A1, A2, A3 until N. Right? Assume we have until AN. And the row column is also same with A1, A2 until we have AN. So then for the diagonal elements, it means A1, A1, A2, A2, A3, A3 until AN, AN. So for our definition of reflexive, it means if we have the A in our AA should always in our relation for all value or elements in our set A. So here, if assume our side have finite elements from A1 to AN, if the diagonal value is always equal 1 for this matrix representation of the relation, it means yes, all of the part of A1 itself until an AN itself is in this relation. So that means satisfy the definition of reflexive relation. Okay, so that's why you can use this rule to check a relation is reflexive or not. And then the second special relation we have is symmetric relation. So for symmetric relation, how we can check is by matrix. So it means if we have the matrix is also symmetric, then we can say this is a symmetric relation. Okay, so then I'm not sure you learned the linear algebra or not. So for the symmetric matrix, it means if we look at the element which is in the opposite position with respect to the diagonal here, then if they have the exactly same value, then we will think they are symmetric. So here, if we use the notation of these elements, it means if we have the elements in the ith row with the jth column, then the elements in the jth row and ith column should also, this pile of elements should have exactly the same value. Okay, so this is also come from our definition of the symmetric relation, because symmetric relation require if AB in the relation, BA should also in the relation, right? So here for AB, BA, if we leave this position, then that means in the matrix, it means we get the elements in the opposite position with respect to our diagonal. Okay, and then let's look at the antisymmetric relation. So the antisymmetric relation, what we have is if there is any element which is in our relation, then the opposite position should get not in this relation. So in other words, should equal 0. So if we have 1 in the position like I row, j's column, then the opposite position like in the j row, i's column should equal 0. So whenever we find a 1 in that position, the position which is opposite with this with respect to the diagonal should equal 0. So here, however, if this position is equal to 0 elements, then we don't care about the opposite position equal 0. If they are also equal to 0, it's total. So this is because for the definition of the antisymmetric relation, we say if AB in this relation, then BA should not in the relation. So we don't care about the hypothesis. If the hypothesis AB not in the relation, we don't care about it. So we only care about AB in the relation which have the position equal 1. We care the opposite if BA is not in the relation. So in the matrix, it means this equals 0. Okay. And so now if we have this example, so we have about this matrix. So let's use this matrix to check, is this symmetric or not anti-symmetric? Is this reflexive or not? So now for this one, if we want to check is reflexive or not, what we need to do, we need to look at the diagonal elements. Are they all equal 1? So for this 3x3 matrix, yes, all the elements here are equal 1. So that means we will have, yes, this is reflexive relation because we have 1, 1, 1 on the diagonal of this matrix. And then let me look at, is this symmetric or is this anti-symmetric? So then we need to look at the elements not in the diagonal. So let's look at the first one. So this is the first row, second column. So if we want to check this is symmetric or anti-symmetric, we need to look at the opposite position with respect to our diagonal. So for this first row, second column, we need to look at the elements in the second row and first column, which is this one. Okay, so now if we look at this pair of these elements, we find, okay, they're in the opposite position with respect to our diagonal, and they are both equal 1. So because both are equal 1, so the first thing we can claim is this is not anti-symmetric. Because for anti-symmetric, it means if one of them equal 1, the other should equal 0. And now both equal 1, so it's not anti-symmetric. And then let's look at the next elements, not in our diagonal, but also equal 1. So this is in our second row and third column. So let's look at the position in the opposite position with respect to the diagonal. So this is in the third row and second column. So here, okay. Okay. So then for this one, with this square coordinate, we can say both of them equal 1. So that means again, if this is element in the position equal 1, the opposite position with respect to diagonal in this matrix is also equal 1. So that means now what we can claim, actually this is a symmetric because in the opposite position with respect to diagonal, they are always equal 1 together. So that we will have this actually a symmetric, this is symmetric relation. Okay, so now we learn how we can use matrix to show our relation. And also we know how we can use the matrix to help us decide if this relation is a special relation as reflexive relation, symmetric relation, or anti-symmetric relation. So hope this is clear for everyone. And in next video, we will explain how we can use graph to write our relation. So see you in next video.